Thank you very much, Hong Wang and John, for having me and inviting me to give this talk, and to the organizers. It's a pleasure to be here today with everyone and tell you a little bit about this fun project we've been working on. Yeah, so to build off a little bit about what Bob was saying at the beginning of the workshop, we're kind of in this situation right now where Harrison Ford was in Raiders of the Lost Ark, where we're up against this big challenge of climate change. We have this big boulder coming toward us, and we need to figure out what to do to get out of the way or to move faster. And part of the challenge for our field is that catalysis is very difficult. It's hard to characterize catalysts. It's hard to characterize catalysts such that we can do representations accurately when we start looking at running DFT and other machine learning models to really know that we have the right surface when we're trying to make predictions. What makes this even more challenging is that catalyst structure is a function of the reaction condition. So when we go over to the beamline, or we run ambient pressure XPS or in situ XFs, the structure of the catalyst is a function of the reaction condition. So what we may start with is, and what we may be modeling in the lab might not necessarily be what is industrial applicable. Additionally, the performance is a function of the reaction conditions. So there was a study done where they looked at electrochemical CO2 reduction, and the Toffel slope, the kinetics, are as much of a function of the copper catalyst as they are of the hydrodynamics of the cell. And this also applies to heterogeneous thermal catalysis. So there's a study done back in 1997 by Fabio Ribeiro and Gabor Samorjai and others, where they looked at various things and how they could, various conditions and how they could affect the reaction rate. So things like temperature, heat and mass transport, crystallite size, all affect the rate by orders of magnitude. And putting all of that into consideration, this was really brought to this paper was brought to my attention by Neil a few months ago. Putting this all together in the report that Neil, Raj, and Rob put together last year or the year before, they showed this example of propane oxidative dehydrogenation on vanadium on silica. And for this catalyst, all these different examples run at 400 C, the measured turnover frequencies vary by 2 orders of magnitude. And so considering the work done by Fabio and co-workers earlier, I'm actually surprised that these rates don't vary by more, considering all those effects. But I think there are things we can really do about this, because catalyst structure really comes down to how you make the catalyst. You should be able to predict catalyst structures based on synthesis conditions, and there have been studies that show that. So for example, specific copper surface area is a function of precipitation temperature and pH when you're making the catalyst. There's been a ton of work done by Kern-de Jong's group, where they show things like drying rate really affect the catalytic structure as we would expect. So depending on the rate that the catalyst is dried, the temperature that the catalyst is dried at, we will see a various particle size. And so all of these pieces of catalyst synthesis are linked together in what we expect will come out. And so then when we look at the performance, we would expect that this is also a function of the synthesis conditions and the reaction conditions. So my group has done some work on tungsten carbide, and depending on how we synthesize the catalyst, so the carburization temperature, the chemical potential of carbon, we can control whether or not we make the beta phase of tungsten carbide or the delta phase WC. And so based on the synthesis conditions, that has a strong effect on the catalytic performance, with one of these phases being active and the other phase not being active. And so we extrapolate this out a little further, not just from experiments in the lab, but when we go into industry, there are more things that we have to consider, more variables, especially if we want to make a real catalyst that goes into a reactor that has an effect on how we can convert some of these new C1 feedstocks into more valuable chemicals and fuels. So something that we tend to not always consider in the lab is what happens when we take a powder catalyst, mix it with a binder, and put it in an extruder. Well, now we have things like mass transfer limitations. Perhaps the binder gets inserted into a zeolite framework, or there are other elements in the binder that then affect the catalytic performance and selectivity. So putting all of this together, we have a very difficult problem where we have to consider the how we're measuring the catalyst structure, how all of these variables when we synthesize the catalyst affect the structure. Then we have reaction conditions can be affecting the structure. And putting on top of that, when we scale up the catalyst, the actual material we have in the scaled up catalyst might not really exactly match what we have in the powder catalyst. It's a very big, complicated system. And so the approach that we're taking in my group, we're starting to think about how we can leverage a lot of these recent advances in large language models that are transforming material science and chemistry. And so large language models have been shown to be able to do tasks like classification, regression, and even inverse design. And so what we are thinking is, well, we can apply these to catalysis to try to accelerate discovery, try to find new materials. And so catalyst development is a really slow process. It takes a long time to develop a new catalyst, characterize it, understand how it works. So rather than try to figure out exactly what the surface structure looks like and how we will in turn determine how that structure affects the performance, well, if we can represent the catalyst with text of how the catalyst is made and how the reaction is run, we should, in theory, be able to develop a function that takes that text of how we ran the experiment to how the catalyst performs. And so within the text of our synthesis procedures, we can put in any variables that we think are important for the performance. So for example, we can definitely put in reaction conditions in with the synthesis procedure, and we can put in things that we think might be affecting reproducibility. For example, where we put the thermocouple in the bed, or if we have a binder present in the system, if we're working with an extrudate versus with a powder catalyst. So to really see how this method of representation works, we wanted to start off in a very low stakes system. So we scoured the literature and we found this data set done by a group in Japan where they did high throughput experiments of oxidative coupling of methane. The catalyst, they studied 59 different catalysts, primarily based off of this benchmark catalyst that's used for the reaction. All the catalysts were made with impregnation synthesis. And what we're showing here is C2 yield, so ethylene plus ethane, versus the number of catalysts that achieve that yield. So just a histogram of the data, and I also have some statistics here. And so it's 12,000 experiments because these 59 catalysts were run at a variety of different conditions. So different temperatures, different pressures, different flow rates. And so the workflow that we're using here looks like this. I'll walk you through it step by step, but it's really divided into a few different sections, where one section we're selecting procedures, running the experiments. Another section, we're taking those experiments that we've run to build up context to run inverse design. And then the last part is we're using the language model to make predictions on those experiments. And what's important here is what we're doing is in-context learning. So we're taking advantage of the context window of the language model rather than fine-tuning the model with a lot of data. And so we start with an unlabeled pool of experiments that we then embed into a format that the model can understand. And what this looks like is something like this. So if we take a subset of that pool of 12,000 experiments, we have the procedures, these are our X values. We have the labels, which are our C2 yields, these are our Y values. And so effectively what we do during the embedding time, we take the synthesis procedure that we write out along with the reaction conditions that are available, we put it into GPT to get this vector representation of the embedding. What's interesting is we looked at these embeddings in a little bit more detail, where we have different sizes of the embeddings. And what we're doing here is we're taking the embeddings, we're just changing the temperature, and we're looking at how the size of the embedding affects the cosine similarity of these embeddings. So for example, if we have an experiment that's run at 850 C, other experiments that are close in temperature should have a high cosine similarity score. There should be a close linear distance between those experiments. And what we see for small embeddings, we don't really see that come across in the cosine similarity, but as we make the embeddings larger, we do see a stronger similarity between similar temperatures versus temperatures that are farther away. And so once we've embedded these experiments into the model, what we do to start out is we need to initialize the model. So we take a random procedure from the embedded pool, And we have that selected procedure, so one of those 12,000. And then if we were doing this in the lab, we would then synthesize the catalyst, run the experiment, and we'd now have a labeled pool that would consist of one experiment where we have that X value, the synthesis and processing conditions mapped to the performance. So once we have that, we then have to start building up the prompt that we're going to feed into the model to then do inverse design. And in building up this prompt, we can only fit a certain amount of context called gamma. So that's the number of experiments we're feeding into the model based on the size of the context window. So the larger your experimental procedure, the more information you're putting in there, the fewer number of experiments you'll be able to put into the context window. So it just depends on how large the experiment is in terms of text. So we start building up that prompt based on this labeled pool. So initially we only have one experiment, so we only have one piece of context, but as we go through this loop, we'll build up more experiments in this labeled pool. So we need to use max marginal relevance to compare the top performing experiment in the pool with other experiments in that pool based on similarity to that top performing experiment to build up this prompt. And once we've built up this prompt, we feed it into GPT and we run inverse design. To give you a little bit more detail on this step of running inverse design, effectively what we're doing, we're taking from the labeled pool, and I just switched the direction on this slide, so now we're going left to right. We take that experiment from the labeled pool, we use MMR to build up context based on a certain number of experiments. So there's a token limit for how much we can feed into the model, so that's going to determine how much context we can feed in, and then we construct the prompt. And so this might look a little abstract, but to show you an example where context is equal to 1, so this is only one experiment showing you here for an illustrative example. I don't want to show you a wall of 12 experiments of what this might actually look like, but we structure the prompt something like this. So we phrase it like a question and answer format. So we say if the C2 yield is the value of the C2 yield for the experimental procedure listed here, then we ask a question if C2 yield is this value times some normal distribution to get some diversity in the model, then the experimental procedure is blank, and then the model reports back with the inverse design of that experimental procedure that it is expected to achieve the desired yield. And so once we have the inverse design experiment, we could, in theory, run that experiment, but here we were starting with a pool of pre-existing data. So what the inverse design came up with might not actually be in the pool. So what we do here is we run max marginal relevance again, comparing the linear distance between the embeddings of the inverse design and what already exists in the pool to come up with a subpool of about 12 to 16 experiments that we then feed into GPT for predictions. And the generative pre-trained transformer will give us probabilities associated with those predictions. And so when we have the predictions and the probabilities, we can run Bayesian optimization to then select a procedure that balances exploration and exploitation. And so just a quick note on this last part. So this is effectively what it looks like when we're asking GPT for experimental predictions when we only have one element in the subpool for illustrative purposes. So we say if the experimental procedure is the experimental procedure written out, then the C2 yield is, and GPT gives a completion with a value of the expected yield along with the uncertainty. And so when we run it for the whole subpool, it looks something like this. And then we run Bayesian optimization using various acquisition functions to try to balance exploitation and exploration to try to identify areas of the space that the model is uncertain about and areas of the space where we expect to have high C2 yields. So putting everything together, the overall workflow looks something like this, where once we run the inverse design, we have this subpool of experiments that exist in the embedded pool. We get the predictions with the uncertainties, run Bayesian optimization, select a new procedure. If we were doing this in the lab, we would make the catalyst and then have the labeled pool, build up the prompt, inverse design, and go around and around. And so what this looks like in practice, again, I'm showing you the data set here, the histogram of the data for these 12,000 experiments. We ran the procedure several different times, several different models. We've run it on the latest GPT-4o model. We've also run a similar workflow where we're using GPR, and in GPR, we're just running Bayesian optimization on the embeddings themselves. And so what we see for these, the example here, is that we're able to, within about 5 experiments, identify greater than the 99th percentile of performing catalysts in this pool of 12,000. And interestingly, running this with GPR gives us very similar results. So if we don't go through the whole language model workflow and we just run Bayesian optimization on the embeddings, we get very similar results. And so this was a really exciting result, and we wanted to extend this further to making real catalysts and doing things in the actual lab. So here we just kind of took what we had in the lab, different metals, different supports, different free treatment conditions to have oxidized catalysts, reduced catalysts, et cetera, different temperatures, and we kept the GHSV fixed. And so we went through the workflow in purple that I described earlier, and we also just picked random catalysts going through a random walk here with the dashed line. And what we found is the initial point was this cobalt, zinc, platinum catalyst in silica. Initially, the model varied the temperature a little bit, maybe learning a bit about temperature, decided it didn't like zinc, swapped out zinc for copper. Again, varied the temperature, decided it didn't want 3 metals at all, went to this cobalt platinum on silica catalyst, where we got 26% yield, which is within 2% of the thermodynamic maximum. And so what's interesting here is all of the catalysts that the model selected contained platinum. And so that got us thinking a little bit about contamination, where perhaps the model already knows that platinum is a good reverse water gas shift catalyst, so it's inclined to include that in its predictions. But it's something that we're digging into a little bit more to try to understand the effect of contamination and how that may affect predictions. And another note I'd like to extend this to before I wrap things up is that this workflow I'm describing is universal. Because we use text as the method of representation, we can apply this method of representation to anything. So we can apply this to adsorbents for carbon capture, where here we're looking at PEI mix supported on silica, similar to the work that's coming out of Chris Jones' group in Georgia Tech, where these samples, these adsorbents are very hard to characterize because you have this complicated polymer mixed in with silica. So representation in an atomistic space is very difficult. So when we applied this same workflow to this PEI silica-based adsorbent, we did something slightly different here. So we ran a few different experiments. We started with just the 2 initial points where we picked 2 experiments from our pool and ran the CO2 absorption capacity in just an autochem, so just measuring how much CO2 these samples can absorb. We did a little zero-shot learning where we just had an experiment, we asked for the model's prediction, and we ran the experiment, didn't do so well. Then we started running the BOICL workflow using these 5 experiments as initial points in the labeled pool. We ran 2 different objective functions, and we see here that when the model makes a bad prediction, so when it predicted around 20 and then the sample didn't really absorb much, it can get stuck around 0. So we ran this BOICL workflow, but then at the end, what we decided to do is just run inverse design. So we could make anything that the model proposed. So we decided, let's just feed all of these experiments in for context, and then we'll ask the model for a sample with a CO2 absorption capacity of 50 micromoles per gram, and then we'll make it and we'll run it. And so we did that for 50, the prediction was okay, 80, it hit it spot on, and then we asked for 100 and it couldn't quite get there. So fitting this all into catalysis workflows, if we're just thinking about how we discover catalysts, maybe what we do now looks something like this. With BOICL, with using Bayesian optimization, with in-context learning, we really think of this as a means to, as another tool to try to discover new catalysts faster, such that we can make new materials to help speed up this transition into the 21st century energy economy with new feedstocks. So with that, I'd like to thank my group, particularly Shane, who did a lot of the work I showed, and my collaborator, Andrew, who's taught me everything I know about language models and really got me interested and excited about this space. So with that, thank you again for having me, and I'd like to take any questions.
Thank you. Really interesting talk. So with the training set used to mostly like consistent data sets produced in one location, or did you consider several small data sets from different sources?
Yeah, so that's a great question. So the data set we worked with was great because it was consistent. It was from one source. Effectively, the reason we wanted to go with this in-context learning with Bayesian optimization is we don't need a lot of data to start. We don't really need any data to start. So we weren't really training the model. We were just using this as a set of data that we knew was clean data from the same place without any artifacts. Maybe it has artifacts. We don't necessarily know that. But then we've applied this to a few other examples. So we've looked at charge transfer across interfaces. We've looked at some properties of steel. We've looked at solubility. And so we can apply this really to many different data sets. The size, we're not so sure yet. Let's say if you have a pool of 50 experiments versus 100 versus 10,000, if you want to do regression, you need a lot more data. You need at least 1,000 data points or so to start doing regression. But for just in context learning, Bayesian optimization, you don't need very much data. I hope that kind of answers your question.
All right, one last question.
Thanks for the super interesting talk. So I found it very interesting that so this method kind of actually learns something from the GPT, because obviously it outperforms random search, right? So do you have a sense kind of what the knowledge it is using from the GPT that helps to do this kind of planning?
Yeah, I think that's a great question. And that's something that we're thinking about in terms of going forward, using open source models like an AnyScale model, such that we can then provide it with our own training data to get a better sense of how that affects things, because we ultimately really don't know what information it's taking in to make its predictions. And I think that's something that's really hard to try to explain. Like we showed with the platinum example, clearly it knows something about platinum, but I ultimately can't tell you what this model really knows about heterogeneous catalysis or how it's making some of these predictions.